some basics in place, let's look at yet another problem on surface tension. So here's a liquid of surface tension T, density rho, and here's a capillary tube. Here's a capillary tube of radius small r. Now the angle of contact between the liquid and the glass capillary tube is given to be theta. Now we all understand that the moment this capillary tube is inserted inside this, then because of capillary action, the liquid will rise up in the capillary. It rises to a height h, as we all know, given by 2t cos theta by rho g r. T is the surface tension, theta is the contact angle, r is the radius of this capillary tube, right? Now, what we want to be able to compute is the amount of heat evolved in rising to this height h, right? In principle, what are the two things that are working here? The two things that are working here are, one, realize that if T is the surface tension, then the glass surface exerts on the liquid periphery a surface tension T circumferentially, making an angle theta with the vertical, right? Making an angle theta with the vertical, this being the contact angle, right? This T that the glass exerts on the surface of this liquid, which is rising up, has a vertical component T cos theta, horizontal component T sin theta. T sin thetas across diametrically opposite points will cancel off. T cos theta acts along the circumference 2 pi r. Do you realize then that this T cos theta is doing work in raising it to a height h? Right? That's one thing. Now, where all does it get consumed? Well, when the liquid rises to a height h, the gravitational potential energy of the liquid increases. The gravitational potential energy of the liquid increases. If h is the height to which it rises, then mg into h by 2 is the increase in gravitational potential energy. So part of the work done by T cos theta into 2 pi r, right? Realize that the force in this direction, let me call it the y direction, is going to be T cos theta, which is the surface tension acting over the circumference of this liquid, which is 2 pi r, right? And this Fy causes it to rise to a height h. So there is work done by this Fy. What is the work done by surface tension, St? Let me call it surface tension. What's the work done by the surface tension? It's going to be Fy into h, right? That's the work done by the surface tension. So what's Fy? Fy is T cos theta into 2 pi r. What's h? H is 2t cos theta by rho g r, the rise of the liquid in the capillary. So which is like 2t cos theta by rho g r, right? That's the work done, isn't it? How much does it turn out to be? Let's look at that. Small r will get cancelled, so which is like 2t squared cos square theta into pi. Oh, it will become 4 because 2 into 2, 4. 4t square cos square theta into pi divided by rho g. This is the work done by surface tension. Part of it gets consumed in increasing the gravitational potential energy, right? How much is that? Work done in increasing gravitational potential energy is mass of this liquid into g into h by 2. Mass of this liquid column into g into h by 2. Mass of this liquid column, which is like, what's the volume of this liquid column? The volume of this liquid column is pi r squared h, right? Multiplied with density, that's a mass, into g into h by 2, right? Yes or no, right? So that's the increase in gravitational potential energy of the system. Where does it come from? Obviously, it comes from the work done by surface tension, right? So essentially then, the work done by surface tension minus delta U must give me the heat that is evolved, in the process, right? So that's what happens to the system. Yes or no, right? So this was again, I thought, an interesting holistic problem, which could be used to understand some more ideas with greater clarity, right? We'll try and look at more problems. This much for this time. Bye bye.